Hello, math students. In this problem, we're going to look for critical points, inflection points, local maxima, local minima, intervals of concavity, and we're going to do it for this function here. And there will be some subtleties along the way that I'll point out, especially when it comes to concavity, especially with this particular problem where we have a high degree polynomial and lots of repeated roots. Okay, so without further ado, let's do some analysis on this problem. All right, first off, we're going to take the first and second derivatives, and we're going to set them each equal to 0. In the case of the first derivative, we're looking for critical points, and remember that critical points are where we'll have horizontal tangents to the function, the graph of the function, sorry. And so let's follow along with that. So we'll have, we take the derivative, we just use the power rule. 5 times 4 is in fact 20. Subtract 1 from the exponent, we get 4. 4 times 2 is in fact 8. Subtract 1 from the exponent, we get 3. And then we're going to set that equal to 0. And once again, this is the function that yields the slope of the tangent line to the graph of this function. So we set that equal to 0, and we'll solve that equation. Similarly, we continue with the power rule. 4 times 20 is 80. Subtract 1 from the exponent, we get 3. 3 times 8 is 24. Subtract 1 from the exponent, we get 2. And then we're going to set that equal to 0, and we're going to look for the inflection points. Okay, now it's just a matter of doing some algebra. In this case, we factor out a 4x cubed, which is the greatest common factor for 20x to the fourth and 8x cubed, and we're left with a 5x minus 2. Then we're going to set each of these factors equal to 0 and simply solve for x. In the first case, we get x is 0. In the next case, we get x is 2/5 or 0.4 if you want to do a decimal. These are our critical points, so here's where we'll have horizontal tangents. In the case of inflection points, we factor out the greatest common factor, which is 8x squared. We have 10x minus 3. And then we set each of these equal to 0. So if 8x squared equals 0, so we just solve for x, we get x is 0. We solve for x here, we get x is 3/10. And these are the inflection points, you'll see. All right, so let's do a little bit of analysis here. All right, so what we're going to do is we're going to look here at f primed, which is 20x to the fourth minus 8x cubed. And we're going to look at its zeros. So we set the zeros of the first derivative there, which are the critical points. And then we want to see where's the first derivative positive or negative. Well, if you use test points, or if you look at this graphically, you can in fact graph the derivative, and you'll see that it is above the axis here. It'll dip below the axis and then go above the axis here. Or you can just do a sign analysis by using test points. A point to the left of 0, a point between 0 and 0.4, or a point after 2/5. However you want to proceed for determining where f prime is positive or negative, that I'll leave up to you. Okay, so here we have the critical points. You'll see that after using some test points or graphing the first derivative, you'll see that the first derivative is positive to the left of 0. It's negative between 0 and 2/5, and after 2/5, to the right of 2/5, it is positive. Well, that tells us that the original function must be increasing, because remember the derivative gives is a function that gives us the slopes of the tangent line to the curve. So our tangent lines are going this way if the first derivative is positive. They're going in this direction if the first derivative is negative, and then this direction if the first derivative is positive. So it means we must be increasing from minus infinity to 0, decreasing between 0 and 2/5, and increasing from 2/5 to positive infinity. All right, and then similarly, we look at the inflection points, and once again, we could do a sign analysis on this version of function or this version of function, or you could just simply plot the second derivative. Either way, you'll find that the second derivative is negative to the left of 0. It's negative between 0 and 3/10, and it's positive to the right of 3/10. So that means our original function is concave down from negative infinity to 0. It's concave down from 0 to 3/10, and it's concave up from 3/10 to positive infinity. All right, so what's interesting is, or what's elucidating, sorry, with doing these sign charts, is you can already see what the shape of the graph is going to look like. Now here's where the funny part happens, or the subtle part, if we want to be a little more, I'll use a better vocabulary, is that it's concave down. There's two concave downs in a row here, right? They're consecutive at this point. Okay, so I'm going to show you a plot of the graph, and you'll see what's happening here. So that means we must be that means we must flatten out here at 0, and then it's going to come down. All right. So let's take a look at that. All right. So here's the shape of the graph, just like we said. So it's going up, comes down, and goes back up again. Goes up, comes down, goes back up again. But the concavity, it is concave down. It flattens out at 0. But look, it's still concave down until we get to 3/10, and then we have a change in concavity here. I tried to line it up as best I could, and it goes concave up. Here we do have a critical point. We do reach a local maximum by the first derivative test, but then once we get to 2/5, we are at a local minimum, and it goes up and increases. So so these two this picture here, or the graph, and the essentially the first derivative test and the second derivative test, which tells us that we're concave down, so we have a local maximum, or concave up, so we have a local minimum. They give us all the information we need. So you have the intervals of increase, decrease, increase, the intervals of concave down and concave up. You have the critical points and the inflection points, and we've answered all the questions that we needed to answer. All right, good luck.